It is another pleasure for me to introduce Patrick Talou. I've been the second originator of the first FIESTA event back in 2014. Patrick completed his PhD in theoretical nuclear physics at the University of Bordeaux, France in 1998. He then joined Los Alamos Special Laboratory as a postdoc in T Division, Theoretical Division, working on quantum physics, nuclear reaction mechanisms, and nuclear data evaluations. He was a staff member in T Division from 2001 to 2018, and from 2018 to 2022, he was group leader in the XCP Computational Physics Division. Recently, he left to start his own company, focusing on science and education while continuing to work for Orlando as a consultant. And his research interests include nuclear fission, nuclear reaction mechanisms, and nuclear data evaluations. So with that, take it away, Patrick.
Thank you, Keegan. Okay. So, hi everyone. It's very, okay, I need to hold it this way. I understand why this happens. Thank you, Frederick, I don't know where he is now, he's over there, for a wonderful first lecture on fission cross-section experiments. Now we're going to go on the theory part. It's always very hard to find the right balance when I'm giving this kind of lecture for the experimentalists and the theoreticians. I will try to find this right balance to talk at a high level and also at to provide some more details. At the same time, I'm going to skip some of the slides, and you'll have plenty of time after that to review them in more detail. And it was working until now, and now it doesn't. Okay. So on the menu, I will just give a few definitions, but I don't need to go really in much detail because Frederick already did it. I will provide an historical perspective of the timeline of different discovery points in fission research, but mostly on the point of view of theory. So I will not talk about every single thing that you could think of, but I will really concentrate on the theory part. I'll make a few general observations about how our understanding of fission cross-section evolved over time and why we needed to evolve our understanding and our modeling of the nucleus. I will then go a little bit more into the formal theory of fission cross-section, which is really based on the R matrix formalism. And I will then go into the phenomenological models and approximations that are commonly used in nuclear reaction code that you probably have heard of, and which are different than the formal theory, but get some approximation based on that. And then I will conclude by discussing open questions and really what I would call the fission grand challenge, which I think is a very exciting thing. And it's very exciting to see so many.
It works now.
Okay.
Yes, page training works now. Sorry, Patrick.
Great. Okay. Yeah, it works. Yep. Thank you. I think it's very exciting it's a very exciting period for fission research. When I started 20 plus years ago, it was kind of a low point, I think, in fission research. And for some good reasons and for not so good reasons. But I think now we have, I think as Frederick mentioned, we have some technological needs that are renewed. And yes, we know a lot about fission, much more than in the 1930s, but at the same time, we still need new, better uncertainties, better cross-sections, better. Fission is very broad, right? So many observables, we need more data and more precise data. But it's also a very fundamental challenge in terms of our understanding of a quantum many-body system. So, fundamental science and application, both sides are pretty interesting and fascinating right now. So it's a good time to get into this field. Definitions and why do we still care? So I don't need to go really much here in any detail. I will just point to a few things. How we are calculating sigma f, this fission cross-section is this lecture. How we are measuring sigma f, that was the previous lecture, and the practical aspects of how we extract fission cross-section from a measurement. Maria and Thanos are going to discuss that in the practical session right after. I will talk about this a little bit later. Frederick mentioned a few things here already. Thermal, thermal and epithermal range, resonance range, end result, and then the fast region here. I will go and try to explain a little bit why we have this thing. Maybe a first thing here, when you see this kind of behavior here, it's not that the resonance structure stops immediately at this particular point here. The reason here is really threefold. One is that we don't have the energy resolution anymore to go and differ and discern the different resonances. There's also a fact that is more open channels are opening, and so the width of the fission cross-section get larger, and so there is a lot more overlapping resonances, and you cannot really, again, distinguish them. And then, I guess the last thing is the Doppler broadening that is happening at these energies. That is very hard to stop. So those three different reasons really conjure to say, well, we cannot resolve them anymore, so we're going to do some kind of averaging, and we're in the unresolved range. Okay. One thing that I find fascinating is that we talk about, but not necessarily enough, we have different entrance channels for fission. Of course, the most known is a neutron-induced fission, and for the obvious reasons, because of the application side, for instance, because of our ability to produce the neutrons and measure this cross-section, because of the magnitude of this cross-section that is much larger than, let's say, a proton-induced fission cross-section by orders of magnitude. But it's very interesting to look at other entrance channels like photofission and transfer reactions like TPF, DPF, which have been used for surrogate reactions, and I will go back to this. Beta delayed fission is an obvious one that is also brings a different set of quantities and of energy, excitation energy and spin regions. Inverse kinematics, Frederick mentioned this a little bit, and heavy ion fusion fission, which I will not talk about today. We are really going to stick to kind of neutron-used, light charge particle and photofission, and low energy fission mostly. So the one thing that when we talk about cross-section, we think fission barriers. And this is what Frederick also mentioned a little bit. This is from the original paper of Bohr and Wheeler in 1939. So we're going back in time a fair amount, and it's fascinating to realize what they knew at the time and what they had. In principle, the whole theory of fission already laid out, and I encourage everyone to read this paper. It's a fascinating paper, and there is a lot of very interesting detail, conceptual information about how to understand this process. So they understood, or they consider that the nucleus was a liquid drop. It's a charged quantum liquid drop. But the idea was it can be deformed, and as it deforms, it has a different energy. So usually what's represented here when we talk about a potential energy surface, it's really the ground state. It's the minimum energy of the system in a particular deformation. Okay? So if we are here at the ground state of the nucleus, we'll be here at a minimum, at 0. Okay? And as we deform the nucleus, there's a competition between the surface tension and the Coulomb interactions. And when you do that, when you calculate, this was done with a Bates-Weizsäcker mass formula at the time, what you realize that when you deform the system, the Coulomb repulsion is going to be lowered, but the surface tension is going to increase. And so at the end, these interactions, this competition between the two creates this fission barrier. I will go back after that to these transition states, but the idea was really from chemistry, and they were considering the probability of fissioning as a kind of a phase space argument of how many transition states, how many channels can be populated when you deform this system. Now, over time, we realize it's a little bit more complicated than this single hump barrier and this pretty simplified picture. And we realize that there is actually some shell corrections that have to be applied for deformed nuclei. And when you do that, you see this is kind of this curve in black here. So the black curve here is a liquid drop, schematic liquid drop potential energy surface. And if you add these shell corrections, you would have some kind of minimum here, which is not usually at 0 deformation. And you will get a first barrier, and a second well, and a second barrier. And you could have even others. That's, again, a simplified picture. But the presence of this second well is extremely rich. As you remember your quantum mechanics 101, it's, you will have a density of states here, and when they reach this level, they are pretty dense. There are quite a few states here. As opposed to here, you will have very few states in this second well. And so the interaction between the two is fascinating for different reasons, for tunneling, for quantum chaos. A lot of very rich physics in it. So a thing that I keep saying, I think it's important to remind people that a fission barrier is not an observable. Okay, we talk about sometimes comparing theoretical barriers to an experimental barrier. That doesn't exist. It's an empirical barrier, okay, so that's extracted from experiment, but it's not an observable. And that's important because when we try to estimate the best barriers and barrier height and barrier width, it's model dependent. It's always model dependent. So I want you to make sure you remember this. So now it gets more complicated because you have these kind of pictures. Nicolas Schenk is here in the audience, and you can calculate this kind of microscopic DFT to estimate what is really the potential energy surface across various deformation parameters. You can also do it through a microscopic approach. The idea here in this case is that you limit yourself to a family of shapes of the deformed nucleus. But what you realize quickly is that there is not just one path. There is not one unique path to fission. There are different valleys, different humps. And so you can see maybe an asymmetric mode, maybe a symmetric mode, and the separating ridge between these two modes. So you can start thinking that, okay, there are different fission modes, different way for the nucleus to deform and to get to its final configuration. And in addition to this, I think I will talk about this a little bit later, but it's important to remember that when you are in this kind of configuration, you're not looking at other degrees of freedom or other reactions that are in competition, like neutrons and photons. If a neutron is emitted here, in a multi-chance fission process, for instance, you are going to have, so this is for 232 thorium, well, you will have 231 thorium fissioning now, so you need to have this kind of side landscape that is going to be also in competition with the rest. So that gets pretty complicated. And in addition, you could have ternary fission. Typically, that would be an alpha particle being emitted at the same time as the neck of the nucleus structures. And so that also complicates the thing.
I just want to get you back to something you said at the beginning, because not everyone might be familiar with what DFT is.
I will go back to this, yeah. But yeah. Density functional theory, so microscopic, so where you start with the nucleons and the nucleon interactions, as opposed to, so you start with what we would consider the basic constituents of the nucleus, right? As opposed to, in this approach, you are deciding that you are going to take the collective effect as the primary metric. Your nucleus is going to be this liquid drop, and you are going to add corrections, microscopic correction to it. As opposed to here, you really start from the nucleon-nucleon interaction. So yes, thank you for mentioning this. You could say that, well, that probably is a better way to do it. It's more precise, etc. It's tricky for fission, and the reason is because here, you are already telling the system, okay, I'm wanting to look at just the volume part, the collective part. This is the main, the most dominant effect that we're interested in, that fission. So why start from the nucleon-nucleon? So both approaches, I think, are complementary and have their own merits and are very useful to help evaluators and our understanding of the process. So following the fission path, I was looking back at this paper in 1989 by Negele, where I was looking at some of the evolution of the nucleus to different shape deformations. And where we are now on this kind of highly computationally intensive calculations of what the nucleus is doing when it's fissioning or it's breaking apart. So this is something from Orel Bulgak and team. And so Orel is going to give a lecture on this, so I'm not going to talk more about this. But it's fascinating to see the evolution of this due to high-performance computers that we can now achieve. And there's still a lot more work to do. One thing that I want to remind people, again, when we are in our group, we feel pretty cozy and we say, okay, that fission, yeah, there is only this thing. But that's just usually one reaction among many. And usually it comes in combination with at least capture, and at certain energies, neutron elastic scattering. You can have charged particles, and you can have, of course, many others. And so when we are looking at this potential energy surface, we are really looking at just one particular open channel, right? And so we have to consider all of these other things. Sometimes in experiments you have to do the corrections, of course, but in theory you really have to calculate everything to be able to get the fission probabilities, which are the ratio of the fission cross-section to the total. Why do we care? Let's say that we know fission cross-section pretty well for many isotopes. These tend to be driven by, again, the applications. Why? Well, we cannot measure everything, and or we don't have time, or we don't have the money, or there are plenty of constraints, right? Or sometimes we don't have the targets. But the applications are going to tell you and are going to drive your answers. Now, in nuclear energy, let's say 1% on the fission cross-section of U5 and PU9 lead to unreasonable safety margin for the past reactors, and for future reactors, like small and modular reactors. So that, I'm referring to this paper, which was kind of a sensitivity calculation based on different reactor types that were thought about at the time. And so you would see, that's a problem, right? We have been operating reactors for a long time. We have been doing other things for a long time with these kind of cross-sections. The point is that we don't have only that information, and that's where the evaluation part comes in, and where integral information that we'll hear on Friday, I think, is going to play a role. So when you do a reactor, you do a mock-up, or you do something that resembles your application, and so you can control your uncertainties and your margins of safety and security much better than whatever you could get from this 1%. Important is other fields like stockpile, non-proliferation, safeguards, astrophysics, medical isotopes. I mean, we have a lot of course, applications of fission. And for this, I will refer you back to a couple of lectures that were very, very interesting by John Leston and Avnit Sood in 2014, 2017. Both of them are in Los Alamos and did a great job of presenting different application examples. So we already learned from Frederick that 1% target accuracy for experiments is very challenging, if not to say impossible. And theoretical calculations, it's also very challenging, if not impossible, from first principles. And I will go through that and why. So here, I'm just mentioning this integral data. And these lectures on Friday are going to really talk about how can we complement our information, our theoretical developments, our experimental measurements, with some other extra information that we can constrain our problem. Okay, historical perspective. Again, point of view of theory only. And it's broad, I'm really trying to limit things, but we'll see how it goes. I start with the discovery of fission, of course, and 1938. And then with these two characters also that we saw, Enrico Fermi from the, again from the presentation of Frederick. Interestingly, at the time, and I will go one past, the discovery of the neutron was 1932, so very, very close to, between 32 and 38, only 6 years passed, and then we discovered fission. In fact, we could claim that Enrico Fermi discovered fission before that, except he didn't realize it was fission. He thought that it was the way they were doing at the time. They were bombarding targets, more and more heavier targets like actinides, and he wanted to build his way through, the nuclear chart. So he wanted to, okay, you send a neutron, it's going to be absorbed, you're going to create a heavier nucleus. That was the idea. So he was looking for transuranic elements. And nobody, some people could, but most people were not thinking that, oh, you send a neutron, a very low energy neutron, to a big, massive nucleus, and it's going to fall apart, and it's going to break up. So not too many people were thinking about this. Ida Nodak was one of them, who said, that doesn't make sense. And the chemist studied right there. Your thing doesn't look like a transuranic. There were some problems with this chemistry. And she was the first one to actually say, maybe it's fission. But okay, she was not listened to. But then they discovered fission, as you saw after that, 1938. 1939, we get these two characters, Bohr and Wheeler, and their famous paper and famous interpretation. Again, I'm really encouraging everyone to go back to this paper because all the basic concepts of fission are in that paper. Later on, we had some fission advice of 1952, Weisskopf again and Blatt. Hill-Wheeler, we'll get back to this, but it's a very convenient way to calculate penetrability of a barrier and then get to the cross-section. Interestingly, in 1956, that was Agabor, I don't know if I pronounce right, but the son of Niels Bohr, who said, wait a second, it's very interesting. We see this in photofission in particular, when you see that the angular distribution of the fragments is not isotropic. And that was very fascinating because you would think that when you have this kind of barriers, you have many, many states that will contribute to the fission channel. And if you have many states contributing to it, you will get isotropy. So the only explanation that he came up with was only a few states, a few of these what we call Bohr transition states on top of the barriers are going to contribute to the reactions. Now, photofission is particular in the sense that you select only a few angular momenta. You don't create a broad range of a broad distribution. So this is very nice because you can really down-select the ones you actually want to populate. So that was a big insight here. Now there was another, so this is experimental, discovery of fission isomers that realize that there are some states that are high in energy and that take time to decay. And there was no explanation for this. We knew about shape isomer at the time, but we didn't know that there could be such a thing because everyone was still with this one hump barrier. And with this one hump barrier, there is no way to have a shape isomer. It's going to decay to the ground state. So that was very fascinating. And 1967, a few years later, Strodinsky proposed this method to actually apply shell corrections to these different nuclei and realize that, okay, now we have this double hump. And that complicates everything. And we love that, right? Because then there is so much more to discover. It was in the 1970s, so Bohr and Mottelson developed their unified model based on also a lot of the ideas that were developed before. They got a Nobel Prize for this. Surrogate reactions. It's one way again of, maybe I should go back. Surrogate reactions is an interesting way in the sense of, again, Frederick talked about the fissile and fissionable or fertile nuclei. And it depends on the neutron separation energy, with what energy you come up. So if you come up with an energy that is higher than the barrier, you are always going to fission, right? The problem with this is that you will never have any insight into the characteristic of this barrier. The barrier height, for instance, you cannot reach it. But if you use that, like a surrogate reaction, like a TPF, where you have a triton and then a proton and you measure both, you can know the energy, the excitation energy of the residual system that is fissioning, but you can also go lower than the barrier, okay? Than you could do with a neutron. So that's very, very interesting. And then in the 1970s, 1980, Eric Lin, who actually gave this lecture on fission cross-section last time around, really developed this R matrix approach of the fission cross-section that I will talk about. And it's really humbling. I've been working with Eric. He's a ton of knowledge, very, very smart and a humble person. has done a lot on the fission. So there are several papers, and I will mention that later. And then there's been some recent work, I would say, using random matrix theory, that would be Weinand-Müller, the chemetrix approach, Birch and company, numerical integration. This we'll hear from Toshiko Kawano later this afternoon. So there's a lot of work happening on fission cross-section theory, measurements. We are still kind of struggling to get to this 1%. And I don't think we'll get there, but I will explain why. And what we can do about it. So these are only a few papers, and as I definitely incomplete list, but kind of retrace what I've been talking about. I'm putting this not for you to look at it, but for you to have this reference when you have the slides. And then a few recent review articles and books. Again, there's been a lot of activity on fission and kind of trying to get to a compendium of knowledge. And so many different people are actually in this room who have contributed to this thing. As a shameless salesmanship, this is this is a book that we edited. Why I'm bringing that up? It's because this came up. I was being asked by the editor, is there something to be done there after we did FIESTA for the first two editions, 2014, 2017? There seems to be like a lot of material that could be making the material for a book. And so we made a proposition and it was accepted. And so we wrote this book, again with many people involved who have been doing the lectures in the past. So anyway, I think all of these papers and books would be interesting for everyone to learn more about this. Okay, so a few general observations. What am I doing on time? 10 minutes. Okay, great. So main features. Here's the U235 neutron-induced fission. I already talked about this. The 1/V region here, which is due to the bound state of the nucleus. The resolved resonance region, which these resonances appear. I mean, now maybe we are so used to seeing this kind of curve, so we just take it for granted. But it's fascinating. At the time, nobody thought that we could have these resonances so close to each other. And it's because of the model of the nucleus we had at the time. Now we realize, okay, there can be this liquid drop, we can have these excited states, we can have this, and it started to make sense in terms of spacing and energy and magnitude. But at the time, it was not that obvious. I already talked about the three reasons that why this thing is kind of an artifact. It's not, in any evaluation, you will actually find that this energy is not quite the same for every nucleus, and it's not the same for every evaluation. And it's because sometimes if we have more information, we'll be able to push a little further. Not that would help the application side, but that could help many other things like, well, it could help anything. I shouldn't take that back. And the fast region where you start having a much smoother behavior, much more statistical in nature because you have all these overlapping resonances. There were a lot of, some questions about standards and ratio measurements before in the previous lecture. So U235 neutron-induced fission cross-section is a standard between at thermal and between 150 keV and 200 MeV. And so the main reason for that, again, is most experimentalists don't want to do an absolute measurement. And by absolute, it's still relative to something. We're still measuring the neutron flux. That's what we need. So usually what's done, it's not a cross-section measurement, it's a ratio measurement between two different foils, for instance, two different targets. And you eliminate a lot of systematic errors this way. So it's very convenient. Now when you try to estimate the uncertainties on this, you have to be careful, of course. You have to convolute the uncertainties coming from the standard, from the denominator. So the point is that you hope that the standard is relatively smooth and relatively well known, because otherwise this uncertainty is going to dominate your final answer. Excuse me. So what's fascinating is that we start seeing this kind of structure. I didn't put which one it is. I think it's thorium 230 or 232. And it's fascinating because here we are in the MeV range, right? And we have these very gross structures of resonances. This cannot be explained by the liquid drop model as a single hump, okay? You need something more complicated. You need to understand that there is some complications in the potential energy surface. Something similar, but at a different energy. Now we are in the EV region. You have this clustering of the fission strengths. This is the total cross-section for Pu240. And here is the fission cross-section. So you see the clustering across, 1 keV and some resonances here with a few 10 to the EV of spacing. Oops. So none of this can be explained by a single hump barrier. So it was this kind of discovery that made people think there's something else going on. We don't know what it is. And it was not until really this isomer, discovery isomer, and the shell correction effects that say, oh, there is a second hump. But again, over time, we started just measuring this kind of thing and saying that just doesn't match with our theory. So it was a very interesting period. I imagine that would have been interesting to be there. At higher energies, that has already been said, when you have enough excitation energy, what you can do is that you can, instead of having fission of the system, of the compound system formed, you will first emit a neutron, and then, so that's what I put n prime here, of a different energy, different angle. And then the residual nucleus is going to fission. Okay? And even higher in energy, again. So during this period where there is no, the cross-section is going to follow the total reaction cross-section. But when you have this, so the fission cross-section tends to go down or plateau, and then you will have suddenly an increase because you have a new opening of a reaction channel which involves fission, but it's not the same fissioning system. So in U235, you create the compound U236, which is fissioning up to here, and then here you start having some contribution from U235 fissioning itself. But it doesn't mean that the probability, the first chance fission is stopped here. It continues, right? You have then to sum these multi-chance fission contributions, all of them at higher energies. And when you calculate this, for instance, or when you measure, there are some very interesting characteristics because sometimes you go beyond the compound system where, well, I will go back to the compound nucleus, what it means, etc. But you can have some pre-equilibrium reactions where you do kind of a scattering and the residual system is not quite left in a compound state. So I mentioned this thing. This was reproduced from 1959. The photofission, again, one photon at a given energy, 6.3 MeV, 7 MeV, and it's the different fittings of this angular distribution of the fragments. Realizing that, okay, if we had too many open channels in fission, the way we would think in terms of this multitude of levels on top of the barrier, we shouldn't see something like that. Okay, so that was really one element, and there is a more recent example collecting many different results, even from SR here, 2017, showing the anisotropy of 0 to 90 degree as a function of energy of the incident neutrons. And again, you see these dramatic changes in the angular distribution of the fission fragments, which tell you that, okay, there is something going on here that is not, that we have to have this kind of resonance structure on the path to fission. I think I will finish I think I have a couple more. Yes?
5 minutes.
Yeah, let me just finish on this. I think it's very quick. That was the cross-section, standard cross-section and ratio measurements. Here, that's the kind of things where, so U238 over U235 as a function of energy, and the same thing for Pu239 over U235. And here you see there is still a cloud of experimental data points, but you can get to a point where we know this relatively well, right? We see the big structures, we even believe that the uncertainty bars is actually much lower than the experimental ones. that would bring a discussion on nuclear data evaluation that is a bit too long for me to explain, but if you have some questions extra on why and how we do an evaluation, that's another lecture, but I'm happy to discuss with you about this. Just to finish on the surrogate data, this is the kind of things where, again, you cannot, for some reason, you cannot measure directly a neutron impinging on a nucleus A to create a compound system B. But what you can create is something different, a different reaction that will leave your system in the same compound system. And same is tricky because it looks the same in appearance in terms of mass, charge, and you can even say in excitation energy you can decide which energy you are studying. So you could say, well, I formed it in a different way, and now I'm looking at the decay. So it should be identical, but it's not. It's not because we are populating different angular momenta, and knowing which angular momenta and parity states are being populated is the most difficult part of any surrogate reaction analysis. And that requires a lot of interesting theory and corrections to be made. So it's very interesting because it can help you actually access some of these nuclei that you couldn't access otherwise, some reactions. But you have to calibrate and you have to be careful of not forgetting something. Here I mentioned, so Younes and Britt in the 70s did a lot of work on this, Britt and back, and Younes started working on this later in the 2000s, and he did a very nice work on this. And then the question is after that is, do you want to combine, can you combine the capture surrogate with the fission surrogate? And capture is even more difficult because it's extremely sensitive to the angular momentum. Okay, so perfect for a break. Except if there are questions, yeah.
Questions. And I'm going to ask a question to break the ice if none is coming. So,
Don't let her do that.
come on. Anyone having a question? You mentioned compound
Yes, there was.
Where?
I'm happy to postpone this question until later. I'm curious about this resonance region that you pointed out a number of times. Are you going to go into more
Yeah.
details about precisely what's going on there later in your talk, or should I?
Yes, I will go there. Yeah.
I have questions.
You mentioned that the sort of large gross resonance structures in the cross-section were not explained by the liquid drop model. Were they completely explained with the second hump
Yes.
theory? Okay.
Yes. So that's related to the same question. Yeah. It's definitely the presence of this second well that creates this doorway state, and the coupling between this what we call the class 1 state and the class 2 state in the two different wells. That's what's creating this interference mechanism and why you can see some of these very pronounced structures. So we'll get there, yes, because it's fascinating indeed.
So you said that introducing the second hump into the model explains the anisotropy. Is that just because there's only certain angular momentum states that you can populate, or?
So actually there are two things. Where am I? Oh no. I should have gone further. Okay, never mind. So there are two kinds of things. There is this double hump structure that creates this interference between the class 1 and class 2 states. Again, we'll go back to this. The states, the compound states that are formed, they are mostly present in the first well versus the second well. But what's going to drive the angular anisotropy is not that. It's what is happening on top of the barrier and what we'll call these transition states. And you're absolutely right. So these states are characterized by quantum numbers like J, K, M. I will go back to this. Populating a particular K state is going to give you a very specific angular distribution. And this is why I'm insisting on, for experimentalists, to measure these kind of things in coincidence with the cross-section, because as we develop better physics models of fission and fission cross-section, we can use that to constrain not only the density of state, but where we populate these things. Again, when we go from different entrance channels, we're going to populate different states with different quantum numbers, which are going to give us different angular distribution. So it's an important constraint.
Just really quickly, you mentioned class 1 and class 2. Would class 1 be the first hump that was discovered chronologically, or would it be the first one that occurs energetically, or deformation?
Okay, so I don't know the origin of the denomination of class 1, class 2 actually. What I know is that, no, it's the first well and second well in terms of as you deform the nucleus, as it goes through this configuration shape change.
Class 1 would have been discovered later, right? Or theorized.
So, well, so the idea at first, when we had just the single hump version of the 1939, there was only one well, right? So there will be compound excited state built on top of the ground state of and the ground state deformation, which is close to zero, right, or small deformation. It's only when we discovered, oh, there is a second well, then we have to distinguish between class 1 and class 2. So I think to be fair for class 2, I think they were discovered at the same time.
That makes sense.
Good, so mini break.
Mini break, yeah. Let's thank our speaker for an excellent first half of this lecture.
Okay, I think that's where we are. Okay, so I'll give a few slides. So here I mentioned the formal theory as being the R matrix approach to fission. And I will discuss a little bit about what this R matrix, if you're not familiar with it, at least on a high level basis. But I will talk a little bit also about how we see the picture of and how we calculate fission cross sections. Typically, we'll take this idea of this independence of entrance channel and decay channel. And this really came with, again, this famous picture of Bohr, where you have a nucleon coming in and in a sea of other nucleons. And what's going to happen pretty quickly is that there is going to be an equilibrium. So the nucleon is going to come in and start sharing energy, excitation energy, kinetic energy with the rest of the neutrons and the protons. And so the system is going to equilibrate pretty quickly. And then the idea is that once it has equilibrated, the system doesn't really remember how it got formed, how it got created, right? So you can really separate these two actions of what comes in and what comes out in two different steps, independent steps. And that's the idea also behind the surrogate reactions, that it really doesn't matter how you come here. Maybe it's a neutron, maybe this triton, and then a proton comes out. At the end of the day, you have this equilibrated system that is going to decay and going to fission, etc. If that's completely true, then we're in a great place. And I see a head shaking. So in many cases, it works. In many cases, it's actually true. But in some other cases, you will have these direct reactions, and you will have you will populate a nucleus not in quite the same quantum state. So that's something to remember. But usually, so the Hauser-Feshbach theory, which is used in all the, again, reaction codes that you may have heard of, like COH, Thalys, Empire, all of these things, they use the Hauser-Feshbach theory, which uses this concept of independence. It's called independence-Bohr hypothesis, and where you basically have a cross-section. I don't know why I wrote this. But this basically, you will have a neutron impending, and then you will have different decays in B channel, let's say. Okay, so neutron coming in, and then a B reaction channel for the decay. And what you're looking at is just looking at the probability of decaying in that. So you come in, you absorb, you create this compound system, and now you are looking at statistically what's the probability, what my probability of going into fission and going to elastic, inelastic, capture, and all of these things. So then the question is how to calculate those, what we call these transmission coefficients. The compound nucleus formation cross-section, again, that's more for your, I don't want to go into too much detail because otherwise I will bore you maybe. And if you have more questions, then we can go in the details separately. Going back to this very simple picture here, again, the nuclear system, and this is a contour plot of the potential energy surface. So basically, the ground state energy at every single deformation. Okay, so if I'm looking here at one particular point, I'm in this particular deformation in beta 2 and beta 4 deformation parameters. What is the minimum energy of my system? Okay, the ground state for that particular deformation. And again, as I mentioned, then when you do that with a liquid drop model, simple one, you get this barrier. Yes?
So what do these deformation parameters mean? Like what does it look like?
So the question is about what those deformation parameters mean. So I didn't, that's a very good question because I didn't plan for showing any shape configuration. I showed early on one with the microscopic plots of Peter Moller, but I didn't even show those deformation parameters. The idea is that if you do it microscopically, then you don't have that built in, right? You are looking at nuclear-nuclear interactions, and then the system is going to deform. But we want to kind of lead it in terms of a quadrupole deformation, so an elongation, that would be the beta 2, right? An octupole deformation, you can have some gamma asymmetry, so where you start having deviation from a cylindrical shape. So all of these deformations, this is just an example of kind of a cut, a cross-section across two parameters. But mostly when we look at the kind of parametrization we need in terms of microscopic, we need 5 parameters to actually fully describe what the nucleus is going through. So again, the mass asymmetry, it can be some different vibrations, and so you need to take into account all the possible paths of the fissioning nucleus. Okay, so the simplest one will be the quadrupole deformation, where you elongate the system. Okay, that will be the simplest. So when you get to a barrier height, again, what you can do is a simple WKB semi-classical approximation to calculate what is my probability of going through this barrier. And what you get is this kind of integral over these deformation parameters, right? Here I should have put the beta 1 and beta 2 across when you are at a certain energy, so these 2 turning points. And you are going to calculate a certain probability of going through this barrier. If you were further assuming that you have an inverted parabola, which is a very common approximation, and it works pretty well, then you can get a very easy analytical formulation, as opposed to here, probably you would have to integrate it numerically. Now it's not a big deal anymore. You could say, well, why don't we do it? Well, we do it now, but it's still very convenient to have an inverted parabola and having some very simple, when you have that, you know, it's two parameters basically to describe a parabola. So you can have this Euler formula that has played a really important role in our way of calculating not only fission cross-section, but also fission half-lives. That's typically what it's used for. Now, very early on, even in 1939, they realized that, okay, we don't just have one state. This, again, you have to consider this hump as the ground state. It's very minimum energy for every single deformation that the system will have, okay? But on top of this, the system could be excited. What that means is that if you come up with an energy that is, here, for instance, a lot of the energy may be tied up in a different deformation, collective parameter. So that means that maybe the energy here, that's not energy available. Because if you're above the barrier, you say, well, the probability is 1, right? We just go through. Here, the problem is that you will actually, most of the energy is going to be tied up in a particular collective parameter, okay? So you won't have all this energy available to just go through the barrier. You will have many different barriers that you could imagine with different shapes across these energies. Okay, now we are going to, there was several questions about this. The way, okay. We have established that fission fragments are not emitted isotropically. It was 1956. Agebor was giving a lecture and realized that, yes, we know if we do some photofission reactions, we are not getting a fully isotropic fragment distribution. How can we explain that? Because if you were to go back here, you will have many states. So how could you have an angular distribution that is so pronounced sometimes? And the only way of thinking about this is that you're not going to populate all these transition states. You're going to populate only a few, and each one of them is going to be characterized by this JKM. I think I have, did things change? Here we go. So I have this plot here where you have the Z, which is the beam axis, right? So you have these neutrons coming in. You have your nucleus that is deformed, which is in the Z prime. And then the angular momentum here. The projection of this angular momentum on these two axes, K and M, will determine a particular orientation for the fragments. And when you see here, again, this is very strong angular anisotropy, denoting that only a few of these states, J, K, M, on top of the barrier are going to contribute to this cross-section. The derivation of the differential cross-section is given here. And these are called Wigner matrices to tell you see they depend on J, M, K, those quantum numbers. And they're going to be very specific. So if you measure the cross-section, and on top of that, you measure the angular distribution of the fragments, it gives us an idea of this. Now, most reaction codes don't calculate that. We need to change that. But that's on the program, and we can start doing this. And again, different entrance channels are going to populate different states. So they are going to lead to different angular distributions. So even if we knew all these excited states, we don't necessarily know them based on a particular reaction. We have to have a host of different entrance channels to actually scan these states. Okay. I'll go back a little bit on this kind of thing. Did we kind of shift this? Here we go. So much better, right? So now we see that, okay, this is a representation of, again, as kind of a porate deformation. It's very schematic, right? You can imagine, and we'll go back to this, but there are many more shape and deformation parameters. But let's imagine you are in one dimension, and now you have this one well, class 1, 2, second well, and then maybe even a third well, okay? Again, schematically. But if the level density, so you'll have states here, excited states, and as you go at this particular energy, for instance, excitation energy, you have a high density of states in the level 1, in this first well. You are pretty high up in energy, the level density is going to be very, very high. Now, on the second well, you will have much less number of states, and they are going to be separated, they are going to be integrable, they are going to be very, very specific. And third would be even lower. You may have one state in one of these very, very shallow well. And so what's going to happen is that you are going to have this hierarchy of states where you have the class 1s, you have many of these states, but then they interact and they interfere with this class 2 compound state. So each time you have a resonance between the two, or an accidental degeneracy, if they are very close, and depending on their coupling, so if they are coupled but lower under the barrier, their coupling is not going to be very strong. If they are higher up and they are just at a level 1, they are going to be strongly coupled and they are going to make a very big resonance. Same thing if you have a third one. And then you are going to have this, again, hierarchy of states, which is going to create this kind of structure for the fission cross-section. So looking at these fluctuations on your fission cross-section is very interesting to determine what's going on here on the path to fission. And now you can get to much more complicated, of course, because here we are looking just at one deformation. Here it's a projection on two different deformation parameters, but this is done with 5 dimensions. 5 dimensions to characterize characterize the shape of a particular nucleus in any of these points along the fission channel. So here it's kind of a projection in one, but you can see that it can take different paths. And here is an example, U236, where you have this, that's the ground state, and then you think, okay, it's going to go symmetric region, but here there is a big barrier ridge, so instead it's going to go asymmetric, and it's going to go more into this well. That's also why there's a difference between fusion and fission, because you cannot go in the same way. So again, that's multidimensional, so that adds to the complexity. Yes?
Yeah, so I actually have 2 questions. Can you say a little bit more precisely why this is characterized as a hierarchy of states on the right here? And also, is there a simple explanation for why the level density in the first well and the second well are so different?
So the second question is, when you have this, I mean, that's really, the quantum mechanics will tell you that you have an increased density of states as you go higher and higher in energy. So if you have, you will have one state here, the ground state, which is not at zero, right? You'll have a ground state here, and then you'll have more and more excited states. And as you go higher and higher in energy, your density of excited state is going to be increased. If you take the spherical harmonic, that's, you have the exact formula for that.
I just don't understand why that doesn't hold for the second well.
Oh, it does, yes. It does, but you see the minimum here is much higher. So let's say maybe there is 1 to 2 MeV difference between this point and that point, okay? And so here, when it's very shallow, then the bottom, okay. So it's just the level spacing, but you are right. On both, in all cases, there is an increase in density of state.
Yeah, and can you just say a little bit more about precisely why is this considered a hierarchy? I just don't understand why you've labeled
that. Yeah. I don't know. That sounded about right. No, hierarchy of states. Yeah, you can call it whatever you want. I think there is no, a state superior to another. It's more.
I think you might be overestimating the sophistication of my question. Maybe I just don't understand what this tree structure is actually supposed to indicate. Like, are some of these states in this tree referring to the second well and some of them are in the first well, or is this all in the first well?
My interpretation came from the French thing, we start cutting heads when we have too much hierarchy. So, so okay. So simply is the fact that you start having coupling. You don't have a coupling directly between the 1 and 3, right? Because you have this, I mean, you could, but especially if you have no class 1, class 2 interactions, and you are right in the middle and there is an accidental degeneracy between 3 and 1, you could have something. But mostly it's going to go through these steps because, but you can have that. It's called doorway states where it's going to increase fission dramatically because of this connection, this resonant behavior. So there's not really a hierarchy of states in the sense of 1, 2, 3. That's all. There is no, but you see that the fact that you have a high density here and that for the same energy, you have much less here simply because the energy gap here between this energy here and the ground state is much lower, right? That's what you have a smaller density, which also means you have this fascinating coupling because these are quantum, I mean, this is chaotic states, right? They are fully in the continuum as opposed to here they are not. And so you have these couplings that can be very, very interesting in terms of the probability of the magnitude and the density of these things.
Okay, I'm not trying to talk to you about that.
Okay.
Thank you.
Sure. And multimodal, okay. So the one thing I want to show here on this slide is simply the fact that fission is complicated. We all know that, but when we start talking about a fission barrier and a fission transition state, you have to understand that it's representing many different potential configurations. In that case, for instance, Broza put some kind of mods. This was actually my plot from something else, but the main reference is here, where you can look at different really significant trajectories when you are in this kind of fission path here. That's a big valley, and that's one going to be a dominant path. And so this is where you will want to know the fission barrier height, right? But it can be many of them. And so you have to consider that it's not just one possible outcome. So you really need to sum over and weighted sum over all of these options. Another one is over angular distribution. So depending on how you slice the problem, you are going to have to reconstruct the total cross-section this way. A multi-chance, see there was a question too, this is maybe a little bit more clear here. So when you go higher in energy, you have the probability of, this is not the way I wanted to write it, okay, I will have to correct it, but so, because I put F, yeah. never mind. So anyway, you have a neutron coming on U-235. It creates this compound system, U-236. And the first chance fission is simply the fact that it's U-236 that is fissioning. Okay? The neutron has been absorbed, and then it's going to create these two fragments, or maybe more. So far, I've been talking only about binary fission. But the second possibility is when you have higher energy in the neutrons, you can re-emit a neutron before fissioning. In that case, U-235 is fissioning. It's not the same because now it's in an excited state. It can have some angular momentum, but mostly excitation energy. And so now you have this neutron and you have this second chance fission. As I was saying, as theorists, you know everything that is going on. You may know the wrong thing, but at least you know. Experimentalists, you don't know how to measure these things versus the neutrons that are going to be emitted after. It's more complicated. And then if you are at higher energy even, you could emit two neutrons, not just one. And now 234 is fissioning. And that's third chance fission. So let's say at 20 MeV, you would easily have that, plus maybe a fourth chance fission. So it means you have to calculate all of them. It's not just one that, okay, we have only this opportunity. At 10 MeV, for instance, we'll have these two things contributing at the same time. And knowing which one is which is tricky. Again, theorists, we know it. We don't know the right answer, but we know something. Yeah. An interesting thing that I wanted to show because it's so cool is that Eric Lin, again, postulated that in 1965. And it's the idea, and I think it has not been studied enough, so that's an opportunity, again, to do something interesting there. It's this N-gamma-F process. The idea is that you come with a neutron, but before the system fissions, it's going to emit a gamma. And what's very interesting about this, so you could have, you create these things, it goes down as a gamma ray, and then it's going to populate something else with a different J and pi. And depending on the particular gamma transition, if it's E1, E2, or M1. And what's going to happen is that then you have different fission probabilities for all these new states that are being populated in the second well. So it's an indirect process of fission. What's very interesting to me, so first of all, it leads to less excitation energy in the system because, of course, you emit this gamma ray. And so you would think that the probability of fission is reduced. Well, not necessarily, because you will have to convolute that probability of excitation energy with what is the probability for a particular state to fission. And it's not just a question of excitation energy. If you populate with a particular M1 transition, for instance, it's going to be populating a specific state that may have a higher probability of fission. So it's kind of fascinating. And here we calculated, so it was like 50 years later, because this was done with just this one hump approach, because it didn't know at the time. Eric Lin wrote this really interesting book, monograph, and at the very end he has this chapter about, there might be a possibility of the two well. And now, 50 years later, we did this paper on calculating this process. And what's interesting here is that what you could do, you could measure the gamma spectrum if you're smart enough, because it's not easy. You have plenty of gammas coming out. So you have to distinguish the gammas coming from the prompt fission gammas, from the fragments, and this one, which is actually from the compound system. So how you can distinguish this, that's a challenge. But it has been done, but I think it needs to be redone and much better, etc. So, but you can study some of the components, like a particular M1 component that show up at some particular energy of the energy range in the spectrum, and it's dominant there. So it means M1 is usually much lower transition probabilities than E1, let's say. But in some cases, that's going to be the dominant factor. So that's a cool thing that we need to worry about. Okay. Any question on this part before I go into the more formal? I have only 10 minutes. I have only 10 minutes. Okay, no question. Wow, okay. So I have to really speed up. Of course, you will have all the slides, so, and we can talk after. Formal theory of fission cross-section is using the R matrix. The R matrix is, but the idea of the R matrix is very simple. you have an internal region. You have a configuration space that is basically separated into two regions. One is the internal region where you have nuclear forces acting, and one with the channels where it's outside of the nuclear range of the nuclear forces, right? And in the R matrix formalism, you will have these particle channel boundaries that is going to be where you're going to do your magic and kind of match the wave functions on both sides of the problem. And so the idea is that you can do an eigenvalue decomposition and build your wave function for the internal region on this state x lambda, which are discrete eigenfunctions and eigenvalues, and they are real if you do this in this R matrix formalism with these particle channel boundaries. I'm going really fast, but so basically from this you can build a collision matrix by matching those wave functions and the logarithmic of them at this boundary. Once you do that, you can recover a cross section. That's the formalism of the R matrix in 30 seconds and in a nutshell. So it's very quick. But the basic idea, and all of this has been developed in the 1940s and 50s by Wigner, Eisenberg, and later Lane and Thomas. And it's a very useful theory for understanding what's happening and how to actually make calculations. It has been extended to fission, and the idea now is, okay, now you have this saddle point. And again, the only reason that this works in that case is that there are not that many channels. If there were too many channels, you would not be able to do this kind of calculations. I will go fast on this. Okay, I'm saying this. So basically, the channels in fission with R matrix they are specified by this mass, charge, excitation energy, spin, and parity of the fragments. Okay. So that's what's going to give you the channels, and so you have to kind of sum up over that. But what's interesting is, again, you are not going to be constrained by that. You are going to be constrained by a much smaller number of these transition channels, these transition states at the saddle point. And that's the magic, because otherwise we'd have a hard time actually keeping track of all of those. This is just for your reading post-lecture, but that's the idea of when you are trying to do a calculation, fission cross-section calculation, you want to know what kind of excitation of the nucleus you want at this particular state. The ground here, it's the ground at the deformation, right? It's not the ground state, but it's the ground state of the deformation potential energy surface at the saddle point. And on top of that, you are going to build different transition states that are just excitation of the nucleus at this particular deformation, okay? Depending on the mass asymmetry, gamma vibration, again, going away from a cylinder, et cetera, et cetera. So you have to kind of know that, and that's not easy. And I've not seen, I think, any calculations really, theoretical calculation of that, because this is also an unstable point. Well, no, there are some calculations on that. I'll take that back, but it's not, I think, used as much in the cross-section calculations. Something interesting here is that when the target spin is very different here between the 233 and 237, you are not going to create again the same population. Here it's 0 plus and 1 plus, and in this case 2 plus and 3 plus. Because of that, you are also going to get this different population, different angular distributions, etc., etc. So this is very rich. The formalism of R matrix has been extended to this double hump barrier, and again, there you have to do this kind of matching at this point. And now there are some really interesting, potentially very interesting physics on, for instance, when does a system acquire this K quantum state, which tells it, okay, it's going to go in this direction versus that direction. We know that there is some K quantum number here, but if this is asymmetric, that we think it is, then K is probably not a good quantum number. When is the direction of the fragment being settled? Because I didn't mention that, but in this potential energy surface here, okay, you go through fission, but the scission point is somewhere here, right? The scission point is when the fragments separate. So why does a channel here is going to determine the exact orientation of the fragment? Well, the idea is that by that time, when it arrives here, it's very well deformed, and it knows its way out. But there is nothing obvious with that. It's, you know, it's kind of the open questions at this point. Now I go to the class 1 and class 2 states. The basic idea here is that, and it's very, we don't have to call them this way, but the idea is that some of these eigenstates in this double well, now some of them will have a character that is much more of they will be much more in the first well versus the second well. And so especially if you are here in the bottom of this well, there's going to be zero contribution or very, very little contribution in the second well. So that's why you call them class 1 and class 2. So the dominance of these particular wave functions in the first or the second well. I really spent too much time at the beginning because this is going to be a bit harder to follow. So, so the Hamiltonian of the full system is this combination of the intrinsic motion at a given deformation, beta 0. So for every single deformation along this fission path, you will have this intrinsic motion of the nucleons. The deformation, so that's characterized by these maybe collective parameters. And then you will have the coupling between the intrinsic and collective. When you do that, you could say, well, in principle, one could solve this Hamiltonian with developing our Hamiltonian on and our wave function on class 1 and class 2 states. And when you do that, you get a matrix like this, which is basically diagonal in the 1, diagonal in the 2, and then you get coupling between the 1 and the 2, okay? And this diagonal element, this off-diagonal element of your matrix and your Hamiltonian is what's going to create all this rich physics and more complication. So in some cases, it can be completely ignored because you have a clear separation between those two wells. And then you can use, or almost completely ignored, and you can use perturbation theory to get there. And so I was going to give you a few examples here. Very weak coupling. So again, when you are very low below the energy, below the barrier height, you can say that the overlap between this class 1 and class 2 is very small. And so the small coupling matrix elements, and you can apply perturbation theory. So what you are getting there, it's a very formal way, but basically your state is almost class 2. Okay, so that is class 2. And then you have a little perturbation over a sum of class 1. Okay? And the same for the energy. You have the energy of a class 2 plus a small perturbation of the 1. And you see that in some particular cross-section, like U238, neutronous fission in the 700 EV region, where you see this kind of component and interference effect between a class 1 and class 2. Again, that's going to be decided by, okay, so I won't have time, by the value of the width and the difference in resonance energies. I'll go through this thing. The point is that you can understand that there is different level of coupling, and when you have this kind of resonance effect that is much more prominent at a higher energy too, you can have this kind of a class 1 that is interacting with more than a class 1 state. So a class 2 that is interacting with more than a class 1 state. You can use a unified Pickett-Fence model, which basically you say those states are distributed in energy, and so you can calculate these things as an approximation. What you get is this kind of transmission coefficients and fission cross-section. Again, I'm not going to go into detail, but the point is that you can see a very big difference between what we call a statistical formula, which is this very basic approach where you have a probability of transmitting through the first barrier and a probability of decaying through fission through the second barrier. The differences are pretty significant here at lower energies, right? I'll skip that. I was going to talk about phenomenological models. So these are what you find in this kind of codes. And maybe that's the kind of code that you are going to interact with. And the typical approximation and solution that they make, usually it's a one-dimensional fission path. Sometimes you get more than one path, or mode considered, but at the same time, this is to give you a bit of higher freedom, degrees of freedom into your fitting process. Usually it's a double barrier with inverted parabolas. Sometimes they are connected, sometimes they are not, in the sense of this second well. And what happens in the second well, usually we have this competition between we can have different things. We can have emission of particles, we can have gamma decay, we can have gamma decay and then return to the first well. So in this case, it doesn't fission. Or it can just go down and then fission, or it can be disappeared. So a typical way of making things disappear in theoretical calculations, you put an optical model, an absorption potential, and you say the flux is taken away. You don't know where it's going, but it's taken away and it disappears. And that's what we use. WKB or Hill-Wheeler expression, and transition states that usually are not constrained by angular distribution data. That's what you will find in most of these codes. There is a little bit of inference from what we know, from the nuclear structure, but there is not a model calculation that is also doing the angular distribution. I think that's really missing. So I don't have time to go into all of this. You can look at this in detail. The kind of things I would say is that you can get a very good reproduction of the data if you have enough information. But if you have nothing, if you have no data, we can be orders of magnitude away from the truth. So it's in part because when you calculate the transmission over a barrier, it's an exponential term. So if you make a mistake of 100 keV here, which is normal, the nuclear masses are no better than 500 keV, let's say. So you can imagine the same thing here. You'll make a mistake of, you will be here. You will be 2 times or 3 times higher. So that's very easy to do. Thalys, at CA, yeah, because CA, they have been developing their own Thalys calculations, and they have done some consistent evaluations of uranium and plutonium isotopes, which is tricky to do. And they also take into account this class 1 and class 2 mixing. COH, I will let Toshiko talk about it this afternoon. So it's an interesting approach to make something completely numerical, but where you actually look at the trajectories in different fission shape parametrization. AVXSF is the code of Eric Lin. So this is really the only code that is calculating this R matrix, using this R matrix formalism in most exact treatment of class 1 and class 2 interferences. The idea there is that you have this coupling, you don't know exactly what it is, but you know, statistically speaking, you have some idea of the distribution of the states and of their magnitude and their coupling strengths. And once you do that, through Monte Carlo sampling, you can actually deduct an average cross-section that was applied. We did that in 2013. It has been applied later on. Do I have 2 minutes more? Okay. And so what I call the fission grand challenge, for me, it's beyond the cross-section, but it's helping the cross-section world a lot. The idea is that we, in the past, we have done very well in estimating some, mostly on the nuclear data evaluation side. We need nuclear data, we need fission data since the 1940s, right? And we've been very good at this because we have been looking at just one piece of the puzzle, and we can fit it. And we can fit it to our applications because we have more information. But now the grand challenge is really to put everything together from a fundamental point of view and also experimentally. I'm not saying that let's go measure everything at once. I think that's what's called the coffee experiment, right? The complete fission experiment. We don't have good coffee. I don't know, it's not going to happen. Because you have some different demanding observables. You want to know the spectrum of the energy spectrum of the neutrons out. You need a time of flight. If you want to know all the neutrons and the neutron multiplicity distribution, you want to capture everything. So we want a very compact configuration. These two things don't go together. So I'm not asking that, okay, we build the most magnificent coffee cup and just do everything there. We can't. But we can measure very specific information very, very well, and then we can put them together with model. But the models, that's our challenge too, is to put this pre and post-fission information together. From the start, when we create the compound system and it fissions, what are all the particles associated with that? What are the fission distributions, fission fragment distribution in mass, charge, kinetic energy? All of these things are linked. So neutrons and gammas, cross-section angular distribution. So we need to start putting things together, not at a level of just an evaluation, okay, we combine them because in an integral experiment. We need to combine them at the physics level. Okay, there's a large HPC are being used now for microscopic calculation. Use of AI, I think there were some questions. Maybe I can answer some other questions on the data evaluation side, but I don't have time for that. But I know that, AI can be used in many different ways. As emulators, for instance, for large-scale microscopic calculations, you don't want to repeat these calculations. They take massive amount of CPU or GPU. And so creating an emulator for that is a fantastic use and an obvious use of AI. Transfer knowledge for different fission and trans channels, that's another one. If you have data more on neutron-induced fission or gamma fission, can you fill the gap? Level densities, there are plenty of things too. Okay, I think you can read all of these things. I don't want to take more of the time now. And I think that I've pretty much described the whole thing. Having this bigger picture, more consistent picture of all fission observable, this is what we are aiming for. And I think for the next generation work, that's going to be pretty fascinating. So I will leave it at that. Thank you.
Any questions for Michael?
Hi, thank you. That was a great talk. I have
Thank
a
you.
question. You mentioned that the angular distribution of the fission fragments aren't currently in the reaction codes. How do you expect when you do input them in, what is that going to affect?
So I wouldn't expect it to be to make any difference in the ones we already know.
Yeah.
Okay, because we know the answer at least for the total fission cross section. But it's going to give us a better understanding of those states that are the transition states that are on top of the barriers. Because there is a lot of speculation about, okay, is this a gamma? For instance, what is the asymmetry of the nucleus when it's at the first saddle point and the second saddle point? We have an indication, we kind of know, but this will put specific constraints on these kind of things. So it's to better constrain one of the parameters of the model if we were to use it. If we are not using it in the model, yes, there is no constraint. So we need to do it.
Hi. So my understanding of our matrix is that it's kind of inherently a spherical model. You have a spherical boundary for your incoming and external and internal wave functions. Can you talk about how that's reconciled with the fission model of Fission, which is kind of by definition deformed and stretched out?
Yeah. So there is nothing that tells you that it has to be spherical. The idea really at the conceptual level is that you have this internal region and this external region that are connected. So this internal region where the nuclear forces are acting, and then an external region or channels, right, that where the nuclear forces are non-existent or constant, or something that we can put that into the asymptotic wave functions. So the question is, how do we do that? What is a radius channel, and how do we define that? And so I would say for the fission extension of the R matrix formalism, it's really more on a conceptual level to some extent, because we are using, we're still using this formalism, but it's at the end of the day, you are just looking at the channels after the outer saddle point, the second one. So that, yeah, we just don't, it's not spherical. That's absolutely right. But it has channels, and so the question is defining those channels precisely.
Question?
There.
Some closer to you.
I just have a quick question. Just the quantum numbers J, K, M. So I guess J total angular momentum, M is the projection, and what's K?
I'll get there. Oh. What? It's too easy. But maybe. No, I got it. Yeah, so I don't know if you see very well here. So J is this I here, actually. So that's the spin. Z is a beam axis, okay? Z prime is the orientation of the deformed nucleus, right? It's passed to fission, so that's the orientation of the deformed nucleus. And so the K is actually the projection of J on that axis of deformation, right? And the M is going to be the projection on the beam axis.
And the axis of deformation never changes.
Well, it is. I mean, the deform. Well, that's yes. That leads to an important question about the K quantum number and what we call K mixing. The question is that we believe that these transition states, once they're populated at the outer saddle point, they are characterized by that. So at the outer saddle point. The question is that is K a good quantum number when it goes to scission, or even is K a good quantum number when you are in the first barrier? So there is plenty of evidence that the first barrier, theoretical evidence, first barrier, it's asymmetric. It's not just quadrupole deformation. In that case, K is not a good quantum number. But so when is K becoming a good quantum number, and is it staying this way? The evidence, experimental evidence, seems to say, yes, we think that K is a good quantum number starting from the outer saddle point all the way to scission. It's keeping this orientation. But it's a very good question. I don't know. That needs to be checked.
Last question.
Yeah, so at one point you mentioned you had a coupling Hamiltonian. How do you determine what form that takes?
What format?
What form it is, yeah.
Oh, okay. That's okay, where is the book? That's a longer conversation. We can talk. Yeah, that's going to be a long answer. There's a lot of details there, but the quick answer, I would say, we make some assumptions on the distribution of states, and we make assumptions on the magnitude of the coupling. So all of these assumptions can be debated. There is evidence for one or the other and how they fit the data, but it's not as neat as I would wish it was. So it's a long. We can discuss. There's a long conversation there.
Okay. Thank you very much for a lively question session for Patrick. Let's thank Patrick one more time.
Thank you.